Okay. Yeah, thank you all for being here again. We are recording this, and hopefully we'll be posting this on the Linda Loring Nature Foundation website at some point, and potentially the Mariah Mitchell Association as well. And the last bit of housekeeping is I'm going to be handing it over to Jay, so I will kind of disappear my screen. But I will pop back up at the end of Jay's talk, and we'll have another, at the very end, we'll also talk about our upcoming speakers in our Science Pub series. So normally, Jay would be the last speaker in our series, but since we're all home anyway for the next little while, in Massachusetts, at least till May 3rd, we decided to do some additional speakers to bring more science content to everybody. So we'll have some additional speakers for the rest of this month. Okay, so with that, I'm going to hand it over to Jay. We're so excited to have Jay, the Mariah Mitchell Association Research Fellow. You're the first research fellow as well, right?
That's right, yeah.
Wow, we're so excited to have you here and hear more about your research, and take it away. And just give me a sec to get out of here myself. Thanks, Jay.
There we go. Thank you so much, Sarah. I'm going to start screen sharing now. That's a spoiler alert. Let's see. There we go. Sweet. I hope you can all see that. And if you see my face in the little corner, that's a good thing. If you want to just see my face, there's an option right above where you see my face hovering. The second button where it says Show Small Active Speaker Video, you can click that and you'll just see me on the side. So Sarah, thank you so much for organizing this. Kitty and Seth also at the Linda Loring Nature Foundation. As Sarah had said, I was going to be the last speaker in the series, and we had to move to the online format because of shutdowns from COVID-19. And so I just want to say I hope everyone is safe at home, you and your loved ones are healthy, and maybe this is a nice distraction from everything else that's going on. And I hope you can also walk away and learn something a little bit about the astronomy that I'm doing here with the Mariah Mitchell Association. So the title of my talk is Strange Extragalactic Signals, ET, or Something Natural. Again, I'm working with the Mariah Mitchell Association, and I got here on an island in September, and I'm going to leave probably early August, and there's going to be a new person that fills in my position studying the same thing. There's going to be another one after that. So for 3 years, there's going to be a person who graduates from college and does this position for a year. At least that's the hope. So, and one last thing before I jump into it. What is it? I forgot already, so I'm going to keep going. So, oh, that's it. If you can't hear me, if I'm moving too fast, say so in the chat. And then Sarah, you feel free to jump in and say, Jay, you're moving too fast, you're moving too slow. And with that, as you can probably tell, I'm a little bit nervous. So we have the drink of the night. It's going to be a shot and a chaser. I know it's not even dark outside yet, but times have changed. So it's called the Fast Radio Burst. It's going to be 1 shot of vodka, chased with Cosmic Cranberry Kombucha. Works pretty well. If you want a mellower mood, just mix some of the vodka and a little bit more of the kombucha together, and you'll have a nice cocktail for this talk. Cool. I'm sure my parents hated seeing that, by the way. So first I want to start, my talk really is about something called fast radio bursts. And I want to take you to a story from the Cold War. Now, as I'm sure you know, in the Cold War, there's a lot of tensions between the United States and the USSR, specifically around nuclear weapons. And in the early 60s, actually before the early 60s, we signed a treaty with the USSR for a partial nuclear test ban. And the United States wanted to make sure that the USSR was complying with that treaty. So we launched something called the Vela satellite program. Multiple satellites in orbit, far, far away, 65,000 miles from Earth. It's actually much further than most satellites are. And what their job was to spy, basically, on at the USSR, and to look for something called gamma rays. These are highly energetic form of light. I'm going to tell you a little bit more about that in the next slide. But this is basically what we're looking for. We're looking for little tiny explosions like this that were indicative of nuclear weapons tests performed by the USSR. And in fact, the viewing field of the Vela satellites could go to the far side of the moon, because that's where we thought that if the USSR wanted to test nuclear weapons, they might even send them far out there. And so there was a good viewing angle of both the Earth and the moon. And what they actually found was bursts, gamma rays happening outside of the Earth, but not associated with the moon. And this is highly unusual. I mean, at first, I'm sure if any of us were sitting in the position of the scientists detecting these bursts, you might be like, oh my God, the USSR has somehow launched nuclear weapons far out into space and testing them. But fortunately, cooler heads prevailed. And what we realized was that they detected 16 of these unusual bursts of gamma radiation. And we knew that they were astrophysical in nature, which means that they were not from Earth. They were some phenomenon that we didn't yet understand. And in fact, these turned out to be something called gamma ray bursts. And since Vela was launched in the 60s and the information was declassified, we've detected many, many new gamma ray bursts. And on the left here, I'm showing an all sky plot. So if you could see, you know how we have a projection that shows the map of the Earth, the surface of the Earth. This is showing the sky around us, the night sky, in what's called the galactic frame. Now you see that wonderful thin disk that's running through the middle here, that sort of line structure. That's our galaxy, that's the Milky Way. And if gamma rays were associated with something that's happening within our own galaxy, then we'd expect them to lie within that little line, that little plane of objects. But instead, as you can see, all those little dots that are everywhere, those are the gamma ray bursts that are occurring all over the sky. What that means is that they're not associated with something in our own galaxy. In fact, they're much further than that. They're associated with objects in faraway galaxies. So fast forward from the 60s to now, we have a much better understanding of what gamma ray bursts are. Again, they involve the deaths of massive, massive stars. And what we could do is a problem-solving strategy similar to how we solved the gamma ray burst mystery to solving this new mystery, the fast radio burst. Now I'm going to take a quick aside. Now you might not know, you might be a little bit lost in saying, Jay, what are gamma rays? What's radio in totality? What does it all mean together? Here's the electromagnetic spectrum. You might have heard of this from high school physics or college physics. It's basically, I don't want you to think about the electromagnetic spectrum. I'm going to think of it as light. That's just what I mean when I say electromagnetic spectrum. Now, gamma rays are a kind of light. There's something called visible light. That's what we can see as humans. There's also radio wavelengths. So radio light, excuse me. That's sort of the lowest energy kind of light. Gamma rays are the highest energy. And in case I haven't been able to impress this upon you, gamma rays are actually very dangerous to us on Earth. They're more energetic than X-rays, like we get when we go to the doctor. And what that means is that we rarely encounter gamma rays in our day-to-day life, which is good, because again, they're harmful to humans, but we can detect them in things like radioactive decay. That's where we have a lot of gamma rays. So we're looking at light. Radio is a light, gamma ray is light, light that we see is also light. So I'm going to focus on radio and tell you about the new mystery that we have called fast radio bursts. The first one we ever detected, it was called the Lorimer burst after Duncan Lorimer, who was an astronomer, who is an astronomer at the University of West Virginia. So he's pictured here on the right. And next to him is another radio astronomer, Maury McLaughlin. They're actually married. And they were both hired together at the University of West Virginia. I think it was in 2006. Now, in their first year at the University of West Virginia, they had an undergraduate student at the college to do a summer project with them to look at archival radio data from Parkes telescope. Parkes telescope, it's a giant radio dish like this. This is a 64 meter, so 64 meters is huge, you can imagine, telescope in Australia that's looking at, for radio signals basically, from space. And what they were looking for was something called rotating radio transients. This is a phenomenon that Maury McLaughlin here on the left discovered. And she wanted to, her and Duncan Lorimer were looking for more of these signatures in old data from 2001 from Parkes telescope. And what they found was an unusual burst in the process. the student that they were working with found a burst that was 5 milliseconds. Just to give you an idea, a millisecond is 1,000th of a second. So really fast, excuse me, faster than we can perceive as humans. And what they were like, the burst was so bright that they were really sort of thrown off. They're like, this doesn't really make much sense. What could it be? They looked at 90 other hours of data looking in the same area, and they didn't see anything else. They didn't see the same kind of signature of this Lorimer burst. And so for a while, it was a really big mystery. And I'm going to explain a little bit more about the signal that we got and what that implies about whatever's causing this burst. So I'm going to tell you about why we think it's coming from another galaxy. Now, I'm going to draw your attention to this plot here on the right. It's showing intensity or brightness versus time in milliseconds. Now, the start on the time axis is 0 seconds, and the end of that axis is 500 milliseconds. So I think that's half a second. And you see this really big peak in the data, and that's the fast radio burst. And actually, in order to make this plot, they had to go through another plot first that I'm going to switch to. So you can see here that it's clearly above the noise. You see all the wiggles on the bottom there on the right. It's a very high signal noise detection, but really they had to look at this plot first. What it's showing here is frequency, that's in gigahertz, versus time since the start of the burst. You see this big black curved bar that's cutting through the data, and that's a signature that we call dispersion. What that means is that light in the radio wavelengths is arriving at Parkes telescope earlier, at higher frequency than lower frequencies, and that's why we get a curve. If this effect didn't happen, what Lorimer would have found is something like this, a black bar that's just straight down, no dispersion. You might be wondering what that black bar that's going vertical across the screen is. That's actually a dead, there's no light there's no detection of light happening in that frequency band. There's an instrumental problem there. So ignore the black vertical bar. I'm just gonna, show you this dispersion effect. Now, gigahertz frequencies, that's where they measured this detection. That's much, much higher frequencies than we get in like our radios in the car. And in fact, usually in the United States, this frequency band, this region of light, you can imagine where radio telescopes look, is mostly reserved for astronomers and sometimes military applications for communication. So what is this dispersion measure that I'm showing you here? What does that mean? Now, we would only observe this curved effect if the source that was emitting this burst that we don't know much about yet came from a really far distance, or there was a lot of intervening material along our line of sight. What that means is that there either has to be a ton of stuff between us and whatever's emitting this, or it's really, really far away. And that's related to the average electron density and the distance. So what they did was when they analyzed this dispersion measure from the plot here on the right, they realized that from our current understanding of the universe, the distance to the source would have to be enormous, something like 3 billion light years away. And that really blew their minds. It sort of blows my mind too. And it's hard to imagine what 3 billion light years looks like. So I'm gonna try to give it a little bit of an understanding of that here. So how far is 3 billion light years? This plot and all the plots I'm gonna show you in the next 2 slides are absolutely not to scale. But on the left here, we have the Earth and the sun. Now it takes light from the sun 8 minutes to arrive on Earth. This is because the speed of light is a constant in our universe. So in 8 minutes, light travels about 93 million miles. So that's the distance from the sun to the Earth. So it's kind of crazy just how fast light travels and how far away the sun is to us. Now our nearest galaxy, that's our neighbor Andromeda, the Andromeda Galaxy. If you're here actually in the late summer and fall, come to an open night, we'll be able to show you the Andromeda Galaxy with our telescope here on island at Loins. The Andromeda Galaxy that's pictured here on the right is 2.5 million light years. So we were talking about light minutes in the last slide. This is light years. So it would take light 2.5 million years to get from Andromeda here. Now, if you had the fastest spacecraft we ever have, and traveled from here and tried to go to the Andromeda Galaxy, it would take you 10 billion years. And what's funny about that is that the Andromeda Galaxy is actually coming closer to us. So the Andromeda Galaxy would get here and collide with the Milky Way. You can ask me a little bit more about that at the end of this talk, before you would ever have a chance to get here into the Andromeda Galaxy at its current distance. The Lorimer burst happened about 1,200 times the distance from the Milky Way galaxy to the Andromeda Galaxy. So even that's hard for me to imagine. And of course, this is also not to scale, but it's an enormous distance. It's coming from some far, far away galaxy. Now back to dispersion. I know it's sort of a hard concept to imagine. So we have this wonderful video of another fast radio burst. And what I'm going to show you here is just, you might need to turn up the audio on your computer. You're going to hear a chirp. This is a audio. Basically, we converted the light and took it and put it into audio for us to understand a little bit better. So I'm going to play this a few times. You can hear it sounds more shrill at the beginning and a little bit lower frequency at the end. There's actually a lot more stuff happening in this burst that I won't talk about. I'm going to play it one more time. And one last time. Totally not pleasant to hear, I agree. But it might help you understand dispersion just a little bit better. So back to the Lorimer burst. That announcement of the Lorimer burst was made in 2007. And for a long time, we had detected absolutely nothing else. No other fast radio bursts were detected for several years. Until 2012, there was another sort of detection made at the Parkes telescope, and that was published from archival data. And they were called peritons. Now, the figure on the right, you might see it shows a plot that's similar to the one that I showed earlier, showing the dispersion effect. And you might say, hey, it looks pretty similar. And that's what was worrying, because peritons that were detected at Parkes telescope, by the way, if you don't know what a periton is, it's some mythical bird from Jorge Luis Borges' novel. We knew that peritons were coming from Earth. And if the Lorimer burst was a periton, that means that it was not an extraterrestrial signal. It was not something coming from outside of our galaxy. You can see that both have dispersed signals, but the hope that we have for the Lorimer burst detection is that it didn't occur on all the beams of the Parkes telescope. Here's what that means. So the Parkes telescope, again, is looking at radio light. It has something called beams. And the best way to understand this is the Parkes telescope, you can imagine its field of view, the area of the sky it's looking at. It's split up into 13 of these circles. Each one of those circles, you can imagine, is looking at a different area of the sky. Now, peritons were detected in every single area of the sky that these beams were looking at, all 13. But the Lorimer burst was detected on just 3. Now, you'd get this all beam effect. The reason we know that peritons are coming from a terrestrial source is that it was happening on all beams, which means that the light had to have been coming from something very local. The FRB, the Lorimer burst detection, happened only on 3 because it probably was an extraterrestrial source. But this is sort of the last hope, that you could see the Lorimer burst on just 3 of the beams. Peritons were happening on all of the beams. So it's been radio silence. And by the way, I can't believe I forgot to mention, one of the authors on the paper about the peritons was Maura McLaughlin. That was Duncan Lorimer's wife. So I'm sure you can imagine that things must have been tense at home for a while, because Lorimer was sort of the only one who was saying it's definitely extraterrestrial. But Maura McLaughlin had pretty good evidence that, no, it might be something terrestrial and it might not be a real detection. So this is a little funny astronomy story on the side there. Fast forward. But the good news is there was finally another fast radio burst detected. And this is FRB 121102. This was detected at the Arecibo Array in Puerto Rico. It's another radio telescope. If you've seen the movie GoldenEye or the movie Contact, you might have seen the Arecibo Array featured in there. This is actually the same fast radio burst that I showed the audio clip from. That's FRB 121102. Now, the numbers that I said there, 12, 11, 02, it's actually a naming convention we have for fast radio bursts. So 12 is a year, that's 2012. The month, 11th month, so that's November the 2nd. That's when it was detected. What's crazy about this is, again, it was 5 years after the Lorimer burst. So Lorimer burst was 2007. This one is in 2012. So it's a long time waiting before where the astronomy community the consensus seemed to have been Lorimer burst was not a real detection. It was some sort of instrumental problem. It was a terrestrial problem. But no, with the new fast radio burst detected at a whole different array, the Arecibo array, it became clear that there was something real going on in space that we didn't fully understand. And what's crazier is that in 2015, the same fast radio burst, 121102, was detected to have repeated multiple times in old data. What that means is the same fast radio burst went off in the same region of the sky multiple times. And so we call it the repeater. Fast forward again to 2018, we were able to identify exactly where the fast radio burst was happening in the sky. This is the dwarf galaxy. I'm showing an image from the Gemini North Telescope that's in Hawaii. It's showing that small circle in the middle, that dark region. That's actually a dwarf galaxy that's 3 billion light years away. Similar distance to the Lorimer burst, but not the same object. Just to give you an idea, this dwarf galaxy is something like 2–5% the size of our own galaxy in the Milky Way. So it's a very different kind of environment than we have here. But the fact that we were able to identify its distance really precisely meant that we could take the observed brightness and the distance and figure out how much energy were we detecting in the radio. And just to give you an idea, this is a sort of a similar thing when you can say, I see a lamppost a mile away. How bright is it actually emitting? Because it's going to be really dim if I'm looking at it from a mile away. And what we figured out was the energy detected from the fast radio burst 121102 in just a millisecond amount of time, it released more energy than our sun does in 24 hours. So it's an incredibly enormous amount of energy that's sort of hard to grasp. So 1 millisecond, it releases more energy than our sun does in 24 hours. And by the way, in 2015, that Periton mystery was also solved. Was it a bird? Was it a plane? What was going on at Parkes Telescope to cause these peritons? Turns out it was a microwave. This is real. Those peritons were really just an astronomer at Parkes Telescope opening their microwave before the microwave cycle had ended. And the magnetron, there's an instrument inside of our microwaves that accelerates particles using magnetic fields to create microwaves. And there's about a millisecond where if you open it too soon, the magnetron has to turn off, and it releases this burst that's very similar to a fast radio burst. So really, it was just a microwave. There's actually a ton of stories in astronomy where people think something's going on, but really it's just someone smoking a cigarette in the same room as a telescope kind of thing. So peritons, that mystery solved. The FRB mystery continues to this day. And I'm showing you here, since then, especially in the past year, we've detected hundreds and hundreds of new fast radio bursts. So on the top there, that's an instrument called CHIME. It's a Canadian Hydrogen Intensity Mapping Experiment. Astronomers have an obsession with fun acronyms. We sort of run out of control with them. But CHIME is a Canadian telescope that's sort of an array, actually, that's been sort of tweaked to hunt for fast radio bursts, especially in the last year. And what they found was 8 repeating fast radio bursts. So fast radio bursts that happen again and again and again. And they found hundreds of non-repeating fast radio bursts. That means they're one-off events and they don't repeat. Or at least they don't repeat so far. Now, one of these fast radio bursts, one of these repeaters, is actually in a spiral galaxy similar to our own home galaxy, the Milky Way. And this is actually a really exciting discovery that was announced at the AAS meeting, the American Astronomical Society meeting in January. And it happened in this very small region. That's what that little green circle that's showing you, that's showing exactly where the burst happened in the galaxy. It was very exciting. There's actually another telescope, the Australian Square Kilometer Array Pathfinder. That's what we work with. That's what Regina Jorgensen at the Mariah Mitchell Association and myself, we work with ASCAP as part of another organization that I'll tell you about a little bit towards the end of the talk. So ASCAP, unlike CHIME, does a really good job of localizing where the fast radio bursts are happening. Now, the one that I'm showing you on the top, the one that CHIME detected with the spiral galaxy, that was one of the few that they have announced a localization, meaning they've identified very precisely where it's happening. HASCAP, the one that we work with, does a really good job of saying, hey, this fast radio burst happened right here, and let's go check if there are galaxies right where we're looking, and see if there's some host galaxy for the fast radio burst. In the future, we're expecting to find hundreds and hundreds, thousands of more, especially in the next few years. And what we can do is we can infer an occurrence rate. We can ask, how often then are fast radio bursts happening in the sky? And what happens is it turns out it's probably occurring about 10 FRBs every single minute. Now, I think I've been talking for something like 20 minutes. So that makes like 200 FRBs, if I'm doing the math right. Someone correct me if I'm not. Fast radio bursts, since I've started talking, have just gone off in the sky. We haven't detected them, but they're probably happening nonetheless. And obviously that makes the mystery even more incredible, because again, that's the similar energy as our sun puts out in an entire day, happening in a millisecond, maybe 10 times a minute. It's really an astounding thing to consider. All right, now I know what you're thinking. Jay, you haven't mentioned what they are. What is a fast radio burst? What's causing the fast radio burst? Is it aliens? Now, it's a question that I've asked myself. It's a question that the media has really been asking, especially in the past few years. Could they be alien spaceships? Could they be faraway aliens in faraway galaxies? Oh, there's a Harvard astronomer that says it could be alien ships. Deep space aliens, oh my gosh, you name it. Everyone, just type in fast radio bursts in Google News and you'll see tons of stories about ancient aliens sending us messages to listen. I'm gonna say that's probably not true. I mean, I could be wrong. I don't think I am. And the reason is that we're pretty sure that these are astrophysical objects. These are some powerful, energetic events that are happening in space. They're probably not aliens. They're not ET. They are something natural. So what do we know? What do we think they are? So there used to be about something like 50 theories about what these fast radio bursts were. And for a while, there were actually more theories than there were detections of fast radio bursts until very recently, as I just mentioned. We sort of have an idea of what general class of objects might be causing something so energetic. Now, a theory would need to account for a couple things: the fact that there are repeating and non-repeating fast radio bursts. We also detect that some fast radio bursts are around really magnetized environments, because we can detect something called polarized light. And what we've sort of come to think about, and I don't want to speak for the entire field, but the recent thesis sort of in the community is that there are actually multiple objects that might be causing fast radio bursts. So there's not one class of object. And here's a good example. On the right here, I show 4 different kinds of objects. All of them have to do with the end stages of giant stars. We have a neutron star, a black hole. Actually, a white dwarf is not a massive star, the end stage of a massive star. It's more the end stage of the end stage of a star like our own. And then on the right here, another massive star death, a supernova. If it was a supernova, that would explain something like a non-repeating fast radio burst, but a supernova is typically a one-time event. There's something called a nova that's related to a white dwarf that could be a repeating event, but a supernova would be a one-time event. So maybe that can explain a non-repeating fast radio burst, can't explain a repeating fast radio burst. So a lot of these theories actually just don't involve one of these objects. They involve the collision of a neutron star, which is another end stage of a star's life, and a black hole, a neutron star, and a supernova. They involve really, really powerful and energetic objects colliding or some other phenomenon. But any good theory, what it does for us is it can predict what we should expect to find in addition in other bands of light. So remember, we're looking only in the radio. We're detecting these FRBs in the radio regime. If we want to really understand more about fast radio bursts, we need to look at where these FRBs, these fast radio bursts, are occurring in other kinds of light. Here's the challenge, though, is that while the radio telescope, if you're just sitting and looking at one radio to the sky, will pick up the fast radio burst, if I'm sitting here at the Loins telescope and I get a call like, oh, we just detected a fast radio burst, can you look in this area of the sky with your optical telescope? So look at light that humans can see and see if you see anything. The burst only lasts a millisecond. It takes me a few minutes to get the Loins telescope pointed wherever an FRB might be. So the challenge is that we haven't detected an FRB in other kinds of light except for radio. Here's where some of the work that I do comes in. We're hoping to study the galaxies that are home to these FRBs afterwards. So we do follow-up, we call it follow-up. We look in other areas of light and see if we can find clues of what causes these fast radio bursts in the environments around which they happen. I'll tell you a little bit more about that in a second. But more on these theories that we have. There's a catalog. If you go to FRBTheoryCat.org, you can read about all these other theories that are out there. There's so many, there's too many for me to list here. And what they do is the website actually does a nice job of saying, does this theory expect a counterpart? Does it expect that we'll also detect an FRB in other kinds of light? And what's helpful for people who are observers, like here at the Mariah Mitchell Association, like Regina and myself, is that that'll inform us of saying, hey, maybe we should set aside telescope time and try to help find an optical counterpart. It's really hard. There's other people who are trying to do that. That's not what I do. But it's an ongoing challenge. But what's helpful about the theory and the observations is they can come together and say, here's what we expect. Can we actually find those things? That's probably going to be one of our best paths forward in finding out what the heck a fast radio burst is. So I'm going to do, this is sort of, we're coming towards the end of my talk, by the way, so hang in there. Despite the fact that we don't know what causes fast radio bursts, I'm going to show you how we can still do really important astronomy research, astronomy science with them. And I'm going to show you this little video. I'm going to try to narrate it for you. It's going to show dispersion, and maybe it'll help give you a little bit a better idea of what's really happening at a fast radio burst. Oops. Whoops. Technical problems. There we go. So, fast radio burst goes off, and in this other faraway galaxy, and here you see the light shown. Its different frequencies are shown by color, which is really helpful. And it's passing through an object before it reaches us, and you can see, because it's passing through this object, it's getting more dispersed. The redder light is going to arrive at us later than the purple light. And it's passing through a few more objects. It's getting more and more dispersed. Finally, it's coming to our home galaxy. Wow, the Milky Way never gets old. There's our sun, and boom. It arrives at ASCAP. Here comes the radio telescope. And as you can see, the purple light, again, it's arriving. The higher frequency light is arriving sooner than the lower frequency light. So what I hope you might have noticed is the more intervening material between us and wherever the fast radio burst is happening will increase the dispersion we detect at the radio telescope. And I'm going to go to the next slide. Sweet. So here's what the research that Regina and myself and our collaborators at the University of Santa Cruz do. We're really interested in asking an important, separate, ongoing mystery in astronomy. It's that we see with telescopes and in wavelengths that we observe in, we see less normal matter than we expect with theory. And what I mean by normal matter is, I'm sure you've heard of something called dark matter. There's much, much more dark matter in our universe than there is normal matter that we can see that interacts with light, like you and me. Now, we know dark matter exists because of its effect on gravity, but our theory right now, focusing more on the normal matter, is that we expect a higher amount of normal matter than we see with normal telescopes. And the awesome thing about radio frequencies is that when we encounter dispersion, it's telling us about how much of that invisible, calling it quote unquote invisible, hot gas, that's really what the matter we don't see, we think it's in hot gas in the universe, we can sort of shine a flashlight through it. So on the left here, you're seeing that the FRB is traveling through less intervening material. So there's a smaller dispersion measure, that's what the DM is. If, however, it encounters a lot of that invisible hot gas here on the right, it's going to be more dispersed. We're going to have the higher frequency light, the purple light, arrive much later than the red light, the lower frequency light. So an FRB dispersion measure is going to tell us how much normal matter the signal had traveled through. And what that allows us to do is it sort of allows us to take a census and see if, because we're detecting in a way that invisible hot gas, maybe we'll be able to find where all the hot gas is located because FRBs are acting as flashlights. Now, there's actually a lot of challenges with this problem that I'm posting here. And one of the biggest ones is we don't actually know how much dispersion is occurring because of the host galaxy right here where the FRB started, how much dispersion is happening because of that galaxy and not just because of the intervening material. We actually have a good, decent idea of how much dispersion happens because of our own galaxy. We want to figure out how much is happening because of the invisible hot gas. One of the big unknowns still so far, the one that we have to, the biggest uncertainty is probably with how much the host galaxy is contributing. So this is one of the last slides I have for you. It's showing that wonderful picture of a galaxy on the right is a Hubble Space Telescope image. There's Hubble of the fast radio burst host galaxy that I've been studying for the past like 8, maybe 9 months. I think this is September. This is the FRB 190608, so it occurred last June. And it occurred in the spiral galaxy of the one that I'm showing you here. You see that red circle that's in one of the spiral arms? We call those spiral arms, and maybe you don't know about galaxies, it's totally okay. It's actually sort of similar, not completely similar, to our own host galaxy, the Milky Way. That's what made it a really exciting project for me as well. Now, the grant that's funding me, that Regina and Professor Prochaska at the University of Santa Cruz, it's funding us to do multi-wavelength follow-up. So I've reproduced the light spectrum on the bottom of fast radio bursts in order to study the cosmic web. Now, the cosmic web is that invisible material that's connecting galaxies. It's this hot gas that's out there in the universe that we haven't detected yet. That's sort of what we call the cosmic web. So that's what I'm studying. And again, it's in partnership with the University of Santa Cruz. And what we're looking at, oh, I might have missed one thing. The image that you're seeing of the galaxy that's from the Hubble Space Telescope way up in space, that's of ultraviolet light. Now in the electromagnetic spectrum image, you see that ultraviolet light, it's less energetic than X-rays. It's more energetic than visible light. Now, I'm sure you guys wear sunscreen. Hopefully you wear sunscreen if you go out to the beach, if you go to Nantucket or wherever you want to go here in Nantucket. You should definitely wear sunscreen. It helps us protect from damaging UV light. The Hubble Space Telescope is also, in this image, is looking at the ultraviolet light from this host galaxy. And the past few months of my work, I'm happy to say we're working on a paper that I've been cranking away at for the past few months. We're hoping to publish soon. We're submitting it hopefully by the end of the week on everything we've been doing the past few months. So that's something I'm really excited about. Here's a quick summary of everything I've talked about in the past few minutes. And I hope that you walk away with, it's that these fast radio bursts are these really energetic events that are a millisecond long. Again, it's a thousandth of a second. They're happening outside of our galaxy. We just don't know yet what causes them. We're soon going to have thousands upon thousands of detections of fast radio bursts. Some of them will have good localizations. That means we'll be able to pinpoint where exactly they're happening. We'll be able to do follow-up like we do and see, hey, what's this galaxy doing? Is it doing anything particularly strange? Is it doing anything that's sort of normal? And that way we can also hopefully build an understanding of how much dispersion occurs from other galaxies, and then do some math, there's actually a lot more than just math that goes on, and try to see if we can find that invisible matter. It's a separate mystery in astronomy that we haven't been able to see yet. And with that, I just want to thank everyone for listening. First, I want to thank Dr. Regina Jorgensen. Regina's been sort of basically my advisor for the past few months here at the Mariah Mitchell Association. I also want to thank Sarah Boyce, Kitty, Seth, for putting some time in and really organizing this virtual talk. there's a bunch of researchers that went into some of the research I presented, the image of the galaxy I'm studying. CRAFT, it's a group over at in Australia that works with ASCAP. That's the radio array that we use to detect well-localized fast radio bursts. And then F4, I can't believe I didn't mention that, this Fast and Fortunate FRB follow-up. That's the name of the organization, the partnership between UCSC, Mariah Mitchell, Nick Tejos in Chile, and a bunch of other awesome astronomers really around the world that are working to solve these problems. And then Jason Hessels, who is the presenter at the last AAS meeting, who sort of inspired some of the things I talked about here in this talk. And of course, I want to thank all of you. And with that, the information for the Mariah Mitchell website is right there. It's an incredible organization that's been doing research and education here on Nantucket since over 100 years now. And my email is also there if you have more questions that I'm not able to answer today.
Great. Thank you, Jay. Jay, can you hear me? You're the one person I can see. So
I can hear you. Yeah, I'm actually going to stop screen sharing.
Jay, thank you so much for that amazing presentation. For those of you who joined maybe after Jay started, what we're going to do now is I'm going to field some questions for Jay. So there were a couple questions asked during the talk. If you have any additional questions, please, you can either use at the very bottom of your screen, there's a little thing that says Q&A, so you can ask there, or there's a chat function as well, and I'll be looking at both. So, one question came in kind of early, so you sort of talked about this with the video that explained it a little bit, but someone asked, what causes dispersion? Is the propagation delay a function of frequency?
That's actually a really good question. It is. It's actually very strongly related to frequency. Let me actually screen share again. I'm going to go back to the slide that shows.
You can keep up the screen share in case there's slides you want to go back to. That
yeah, that's actually a really good point. Let me screen share PowerPoint, share, and so that's a really good question. It's very strongly tied to frequency. So dispersion is really caused by, if you guys remember, something called the index of refraction. The index of refraction is what causes when you look at underwater. If your head's above water and your body's below the water, you might see that it looks like they're disconnected, and it's because of an effect that the change in the density of material has on matter. So there is more dispersion that occurs. It's very strongly dependent on frequency. That's a good question. Yeah, I hope that answered your question.
Okay, so then the other question we had was from Val Hall. Do you have any idea what the role of the gamma rays are in DNA mutations and thus in evolution?
That's a good question. I have a friend, Katie Chapman, who's part of the RU that I did here on Mariah Mitchell 2 years ago. Katie's really an expert on cosmic rays. Now, cosmic rays, when they interact with our atmosphere, some of them release gamma radiation, and they do cause, I believe they do have an effect on DNA mutations. Now, cosmic rays are thought to have influenced the evolution of human life through the radiation effect that they have on DNA. I suspect gamma rays probably have something similar to do. I wouldn't recommend to go around and trying to mutate your DNA with gamma rays. It's more likely to cause more damage than any good.
Sorry, I didn't want to interrupt you if you have more.
Oh, that's what I have.
All right. Does Jay think that the repeaters could be interactions with black holes and other objects?
That's a good question. So if the repeating fast radio bursts are because of black holes, I would suspect they have more to do with the accretion disk. So when black holes swallow up other objects, they have a disk of material. If you've seen the movie Interstellar, that does a really good job of showing the disk. That's the part that's bright in the movie Interstellar around Gargantua. There are a few theories that think that something called active galactic nuclei, these are the supermassive black holes that are at the center of galaxies, may have something to do with some fast radio bursts. Now, these have huge accretion disks. They have a lot of accreting material towards the center black hole. That's one of the theories. And off my head, I can imagine that maybe a repeating fast radio burst has to do with that disk of material, because that disk of material doesn't go away immediately. The reason I'm hesitant to say that it's those black holes is that my understanding, again, I'm not a black hole physicist, I really don't study black holes, but active galactic nuclei, which are sort of thought to be one of the things associated with fast radio bursts, the reason why they might not be the cause of FRBs is that we, through some of the research we've done, is that we found that some of these FRBs are happening outside the center of the galaxy where those active galactic nuclei, these supermassive black holes, are thought to be. So I suspect that FRBs, or maybe even repeating FRBs, may not be because of supermassive black holes, AGN. But again, excuse me, I am sort of agnostic to some of the theory, but I'll try my best. I'm sure that's really what most people are interested in, what's going on. But I sort of walked around the answer on that one, but I hope that gave you a little bit of insight.
That's good. And just so you know, too, I think through the recording, we'll have a lot of these questions. So I think, we can always go back to
Cool.
if you think of other answers or want to follow up on anything.
That's a good point, yeah.
Okay, so has a strongly lensed FRB ever been detected? Also, can we expect to see a gravitational wave counterpart to FRBs? And do we have an idea of what that would look like?
That's a really good question. That's from, I think it's from Katie. That might actually be a friend of mine that I think I know. Great question. I'm actually not sure. I remember there's a lot of talk in some of our collaborators at ASCAP who are a little bit more on the theory side of fast radio bursts. There is prediction that some theories have that gravitational waves should be detected with FRBs. To date, there has not been one that I know of. So that would be a game changer if we detected FRBs with a gravitational wave counterpart. And by the way, if you don't know what gravitational waves are, that's a whole other field of astronomy. There's something called LIGO that's detecting, it's like this huge mile-long facility that detects how space and time can contract, and sort of when it interacts with something called gravitational waves from the collisions and of giant other objects like supermassive black holes or black holes. Do I have any idea what that would look like? I don't think I do. Sorry.
All right, we have a few more. We have like 3 or 4 questions. They keep coming. Why do you think the quote unquote invisible stuff between galaxies is hot as opposed to cold?
That's a really good question. I think that's from Georgia. Georgia was actually an RU student here at the Environmental Association this past summer. So why do we think the invisible stuff between galaxies is hot? That's because cold material. So let me start with the first idea is that if material is mostly cold, we think it's probably mostly made of hydrogen and other material, and it usually condenses really well. And what that causes is that dense clouds of hydrogen and a few other elements are mostly found in regions like galaxies. We don't typically find cold regions of material. Actually, that might not be entirely true, but outside of galaxies, because there's a lot of densities that are required. There's a higher density that's required to make. You need a lot of material to get cold regions of material. And here's the other thing: electrons, free electrons. So that's electrons that are ionized. So ionized material is what leads to the most dispersion in radio wavelengths. So atoms that are a partner of electrons, neutrons, and have a full molecular structure, they will cause less dispersion than free electrons in space. And now free electrons are usually from really, really hot gas that's out in space. And that's why we think dispersion mostly caused by hot gas rather than cold gas in space.
All right, I have another question. So this one is, I understand that the speed of light is a constant. However, purple in your example reached the Earth sooner than the other light. Is some light slowing down? And if it slows down, the light does not actually have a constant speed, does it?
That's a really good question. So the speed of light is constant in vacuum. This is actually a little detail that I sort of skipped over and that maybe I'll take a second to mention densities in space. So on Earth, the density of material at sea level is something like in 1 cubic centimeter. So if you have a centimeter, a little cube that's the size of a centimeter on each side, inside that cube, there's something like 10 billion times another billion. So a billion times 10 billion molecules within that 1 cubic centimeter on Earth. In space, in vacuum, so near vacuum, space is actually not empty. Space is not entirely a vacuum. In the hot regions that I'm interested in, that are causing this dispersion, the density can be as low as 100 electrons in 1 cubic meter. So in a whole meter, there's only 100 free electrons, 100 things, really, as opposed to 10 billion times a billion in 1 cubic centimeter on Earth. Now, the speed of light is constant in vacuum. So when there's absolutely no material whatsoever that light interacts with, it travels at the speed of light. There's actually a slight difference when you go from one material to another. So the speed of light has sort of like a maximum limit, I'd say. Now, if Regina or anyone else wants to jump in and correct me if I said anything wrong, please feel free. But the speed of light is constant in vacuum, and space is in a perfect vacuum.
Excellent. Thanks, Jay. All right, and then, excuse me, from the dispersion data, can we distinguish the scenario that the sight lines, sorry, from the dispersion data, can we distinguish the scenario that the sight line is penetrating a big cloud at one redshift or many small clouds at different redshifts?
That's actually a really good question. So I'm actually going to jump out of my slides and I'm going to go to another one. So while I talk about that, I'm going to talk a little bit about redshift. Redshift is a way for us to understand distance in astronomy. Very large redshifts means we're looking much, much further back in the universe. So towards the beginning of the universe would be a really, really high redshift. The galaxy that I showed, the one that I'm studying, is at redshift 0.11. That's actually it's relatively close, pretty far for us, like I said, billions of light years away. So redshift is a way of talking about distance. So the question is, from the dispersion, can we figure out if the sight line, the way that we're looking, is going through one of these invisible hot clouds or more than one, and if they're happening at different redshifts? That's a challenging question, and that's actually one of the things where I think some researchers are trying to figure out, is that can we figure out how many different things we're going through? The best way we have to do that is look at other astronomical data that might suggest maybe there's a galaxy that's along this line of sight where we can associate some of the dispersion to. That's probably one of our best ways to distinguish whether we are going through more than one cloud or more than one redshift at multiple distances. So we can't do it with the dispersion data alone. The other related question is, can we figure out if we're looking through multiple material? There's another effect we can observe in the radio wavelength. It's called scattering. So some of the light, in addition to being dispersed, it experiences an effect called scattering. I'm going to sort of glaze through this real quick. We actually, if you're familiar with something called gravitational lensing that I think Katie was asking about, there's more lensing if you're halfway between whatever's causing the light and the person observing the light. We actually observe more scattering if you're close to the middle between the source emitting and the source receiving. That's us. So using scattering, we are actually able to do some inferences about where intervening material might be. The question about whether there's multiple material, that's actually a really good question. I'm actually not sure how to answer that.
So I just had a quick question of, I know you said you're going to be here through your fellowship through August. What is in store for you after August? Are you going to continue with this line of research?
That's a really good question. So if you ask me again at the end of the week, I think I have to decide on a graduate program to go to.
Exciting. I didn't even that wasn't like a seeded question. I really.
Oh, no worries.
No pressure.
Yeah, I think I've narrowed it down to one or two schools, and I think I'm going to hold my
don't say this is
tongue until then.
Broadcast across the. No. Well, thank you. Oh, the very last question was, where do you buy cosmic cranberry kombucha? That wasn't my question.
Oh, that's a really good question. So if you're on Nantucket, if you go to Stop and Shop, there's if you know where all the meats are, between the meat section and the section with the toilet paper, there's like a on the short end. You know, if you imagined each aisle was like a rectangle, on the short end of the rectangle, there's a little section that's refrigerated. You find tons of kombucha there, and that's where you'll find Synergy's, GT's Cosmic Cranberry Kombucha. It's great stuff. I love it a lot.
Very popular aisle these days between the toilet paper and the meat.
That's right.
Well, thank you again so much, Jay, for being our inaugural virtual Science Hub presenter. I'm used to everyone clapping at this point. We're always like, yay! So it's funny to me too to be hosting in a virtual framework. So thank you for everybody being here. I just want to give a little heads up. Oh, you already even have the next Science Hub. Nice job. Oh, look, in the chat, people are clapping and saying thank you. So.
Thank you. Yes, it really means a lot.
For those who are still on, we hope that you can join us next Tuesday, April 21st at the same time. There'll be a new Zoom link that we'll be posting both on our website, on the event page, as well as on our Facebook page. And it's going to be me. I'm going to be talking about a project that we've been working on during our stay-at-home orders. We've been doing our LLNF BioBlitz using iNaturalist. So we'll be talking about what people have been seeing so far during our BioBlitz on Nantucket and how to use iNaturalist generally. So if you're not on Nantucket, you can still learn about using this really easy citizen science program to help you identify all the biodiversity around you. So if you're an astrophysicist on the West Coast and you're like, why would I ever go to this talk next week? We're going to be talking about how you can, during our times outside, learn about what's around us. And we're going to be talking about too also the leaderboard so far for our BioBlitz, and that's both the people that have been looking for creatures, but also the creatures themselves and plants. Who's winning, plants versus animals? It's an age-old question. And then rounding out our April Science Pub, using my cheat sheet here. On Monday, April 27th at 4 p.m. We're going to have Mass Audubon's Nantucket Sanctuary Director, Sam Kefferstan. So Sam just joined us on Nantucket as the Sanctuary Director in December. So we're excited to hear from him. He's going to be talking about Mass Audubon's Coastal Waterbird Program. And so there'll be more information forthcoming on that on our Facebook event page and our website as well. So thanks again, Jay, and thanks to everyone who joined us. And yeah, I guess we'll see you next week.
Thank you. Looking forward to it.
Thanks, everybody.